Hello class and welcome to lesson 3.5. Today we're looking at solving quadratics. Before we get to that, let's just do some warm-ups to refresh our brain on radicals. We see radicals when we use Pythagorean theorem, as well when we use the quadratic formulas, where we're going to extend on to that today. All right, so start off with our warm-up. First thing we're going to do is simplify. Okay, so taking a look here. Simplify mean, oops, sorry. Somehow my smartboard's acting funny. Let's see if that will undo itself. There we go. Let's try this again. So again, when we're simplifying, it asks you to multiply. So multiply, you may also see as a dot, I think in your textbook, I can't remember, but a dot means also to multiply. So 5 times -2 is -10. Root 3 times 4, which is 12. You can then simplify that. So it's going to be -10 times root 4 times root 3, which equals -20 root 3 when you bring the root 4 over, or out, okay? All right, next example. I'm just going to show you a variation of how else you can do this in the second example here. So I've got root 3, and I'm going to break that down because currently I can't subtract these because they're not like radicals, okay? So I'm going to go 49 times 2 under the square root. Subtract 5 times 36 root 2 times 2, okay, under the square root. Then what I'm going to do is realize that, hey folks, 49 is a perfect square, so when I bring that out, it's going to be 7 times 3, which is 21, and I still have root 2 left over. Okay, looking at my next expression, again, I've got 36 under the square root. I take it's a perfect square, so it's going to be 6. So 6 times -5 is -30, and I have root 2. Notice now, ladies and gentlemen, that they are like radicals, so now we can add and subtract. So 21 subtract 30 is -9 root 2. All right, moving on. You're going to take -3 root 3 and cube it. What we need to do is expand that out because we have to take -3 root 3 and times it by itself 3 times. Okay, so a negative times a negative times a negative is going to equal negative. Okay, 3 times 3 times 3 as our whole numbers is going to be 27. And then root 3 times root 3 times root 3 is going to be root 27. Okay, again, we can break up root 27 into 9 times 3. The 9, ladies and gentlemen, is a perfect square, so we bring it out. So 3 times -27 is going to equal -81 root 3. All right, moving on. We're going to expand in D to make it easier. Okay, so we're going to use our expanding laws. Okay, so it's going to be 2 root 36 plus 6 root 16. Okay. Then, ladies and gentlemen, realize that those are perfect squares. So you have 2 times 6 plus 6 times 4. So you have 12 plus 24, which equals 36. There is another way you could have done this if you were using the BEDMAS rules. I would have also accepted this as a solution. Okay, leave the root 2 out front to start with, and then we can simplify. I'll just rewrite the question first. Okay, and then we're going to look within the brackets here if we can get these to be called like radicals. Okay, so let's just move this up. So taking a look, we have 2 root 2, and then we can simplify this to root 9 times root 2 plus 3 times 4 times 2 under the square root. Okay, and then we're going to bring out our perfect squares out. So we have 2 root 2 times 3 root 2 plus 6 root 2. Now these are like radicals, so we can now add them, subtract them. So if we're following BEDMAS, this would be 9 root 2, and then it's a simple multiplication to end this off. So 2 times 9 is 18, root 4. Okay, root 4 is a perfect square, so it's going to be 2 times 18, which equals 30. 6. So again, there's two answers for that one. This one might be a little tricky, this E. Okay, how do we simplify that? Well, first of all, we could recognize that, hey, it's d to the 4th times d. Okay, and then you take the square root of d to the 4th, which is going to be d squared, and you're left with root d. That's one exception. Or you could just apply it to the exponent laws, where you have the root of d to the 5th. You could just tell me that, hey, since this is root 5, but the whole thing's raised to the exponent 1/2, that could simplify to d to the power of 5 over 2. I would accept that also as a simplification. All right, hardest one, here we go. Taking a look at this, ladies and gentlemen, we have 5. Now we've got n. It's the root of 2, but it's raised to the 7th power. So again, you're using your power of a power laws. So how did we get 7 over 2? It's 1/2 times 7, which gives you 7 over 2. Subtract 2n, and again here it's going to be to the power of n to the 5 over 2. Okay, looking to simplify, ladies and gentlemen, we've got 5n to the 7 to the exponent of 7 over 2. Subtract, now using your power, using your exponent laws, remember n is really to the power 1, which is 2 over 2. When you multiply, you add. So that's going to be minus 2 to the negative 2 to the negative 2n to the power of 7 over 2. So now we have like radicals, ladies and gentlemen, and we will end up with 3n to the 7 over 2. That one's a tricky one. And again, you have to recognize that first of all, it's the power of a power law, and then your multiplication law. And remember that when you have powers at the same base, you add the exponents to get you your 7 over 2 there. All right? So those are the warm-ups, ladies and gentlemen. If you need any help, please come and see me. Now let's move on with today's lesson. Today's lesson, we are going to solve quadratic functions. In order to solve, that means you need to find the variable. So usually you're going to find x, or the variable. Okay? And there's two ways to do this. Number one, you can factor when it's easy. And if it's not easy to factor, you're going to use the quadratic formula. So I'll call that quad formula. Okay? All right. Let's take a look, ladies and gentlemen. Example number 1. It says to determine the roots. Just remember, folks, the roots are the same as the x-intercepts, as the solutions, as the zeros. They all mean the same thing. Okay? So taking a look, we have to use the zero product property. In this case, I think it's going to be easier to factor. So I'm going to say, hey, I've got to factor the x out. So we're going to have x plus 4 equals 0. Okay, and you should remember last year when you used the zero product property, in order for the left side to equal the right side, that means each of these products must equal 0. So either x equals 0 or x plus 4 equals 0. Solve for x here, x equals negative 4. So therefore, the roots are 0 and negative 4. All right, looking at our second example. Okay, we want to get everything on, collect the like terms on one side. So we'll go 2x squared, bring the 5x over becomes negative, and bring the positive 3 over becomes negative, and we're left with 0 on the one side. We need that in order to solve. Okay, looking at this, ladies and gentlemen, it looks like we're going to do decomposition. So product equals negative 6, sum equals negative 5. Okay, so what we're going to have is our values are going to be negative 6 and 1. So over on the side here, we're going to go 2x squared. Remember, you split the middle term, so negative 2x plus x and plus 3. So again, you split that middle term. Okay, then you're going to factor by grouping. So what's common here? So we have 2x, and when we take out, we have left with x minus 3, and then plus 1. x minus 3. I apologize, folks. I forgot to change the sign here. I was looking at my original question, so please fix that up, okay? Sorry. All right, I was looking here instead of here. This is where I should have looked, okay? So my fault for that. All right, now let's finish this. Our common binomial is x minus 3 times our leftovers, which makes the second binomial. That, in fact, goes here, so we now have x minus 3 times 2x plus 1 equals 0. Okay, let each factor equal 0. So x is going to equal 3, or x is going to equal negative 1/2. Okay, again, if you need to show that work, I'll show you on the side. Remember, 2x plus 1 equals 0. 2x equals negative 1. Divide both sides by 2. So therefore, I just make that our margin there. Therefore, our roots are 3 and negative 1/2. Hey, Deetsy, how's it going? Good, you're in my video. Good. Mr. Dietz loves math, everybody, and he can't wait to solve quadratics. He absolutely loves it. All right, class, let's take a look at this third example. Look at this third example again. Let's get our quadratic all on the same side. Okay, equals 0. We look for our product. Our product is negative 2, and our sum is negative 6. Can we come up with any factors? No, there's no factors here. So as soon as you do no factors, therefore you're going to use the quadratic formula. Okay, and again, ladies and gentlemen, if you can't remember the quadratic formula, I'll write it out here. It'll be provided on your test if you need it. So it's x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay, so just for those who may have forgotten, a in this case equals 1, b equals negative 6, and c equals negative 2. So let's sub it in here and solve for our roots. Okay, so subbing in, you're going to have x equals negative times a negative makes a positive 6, plus or minus negative 6 squared minus 4 times negative 1 times negative 2, and that's all over 2 times 1. Okay, use your calculator or your brain power. Solve within the quadratic or the square root. Okay, and hopefully you end up with the square root of 44 all over 2. Okay, this is where things get different, ladies and gentlemen. In order for us to properly identify radicals, this is why last day's lesson was put in here. We're going to realize that, hey, we can break this down. It's not simplified enough. So that's going to be 6 plus or minus 4 times root 11. Okay, or root 4 times 11 under the square root. Bring that out. So it's going to be 2 root 11 over 2. And what you need to notice here, folks, is the reason we do that simplification is because now all terms can be divided by 2. So 2 goes into 2 once, 2 goes into 6 3 times, and 2 goes into 2 once. So what we're left with is x equals 3 plus or minus root 11, all divided by 1. Okay? So we break it into its two cases. So either x equals 3 plus root 11, or x equals 3 minus root 11. Okay, so plugging in your calculator, you should get an answers of x equals 6.32 and x equals negative 0.32. All right, so therefore, roots are 6.32 and negative 0.32. So in this case, guys, you wouldn't be able to find any factors, and whenever you get a decimal answer, you could easily tell that you can't factor. Okay? All right, and someone might ask, hey, Mrs. R, can we use the quadratic formula even if it's factorable? And I'm okay with that as long as it doesn't say use factoring to develop to find your roots. Okay, All right, so you can choose either method, but quadratic formula will always work. However, factoring will only work when you have even factors, or even roots, not like this last example we just did. All right, let's take a look at a word problem now. Okay, example 2. The flight of a baseball can be modeled by the function h at t with that equation, where h at t is the height in meters at t seconds. How long will it take for the ball to hit the ground? Well, the first thing I like to do is, hey, what form is that quadratic given in? It's given in standard form. So what does that tell us initially? We know that the c value is 0.5. So my y-intercept equals 0.5. What does that tell me? That tells me the initial height of the ball. So therefore, okay, the baseball was initially 0.5 meters high when it was hit. All right, so it gives us initial height. Okay. Now, in order to take a look at finding when the ball hits the ground, okay, let's just draw a quick sketch of what we know. We know initially the ball was hit at 0.5 meters, so this is 1 meter here. We know it was hit at 0.5. The ball's going to go in the air and come back down, okay? And instead of having x and y, at this time you have t and h. What we're looking for on our graph is how long will it take for the ball to hit the ground. It hits the ground when the height equals 0. So we're looking for the 0 or the x-intercept. All right. Notice, ladies and gentlemen, that if we were looking for the other symmetry point along here, it's going to be a negative value. We're not interested in that one. So when we solve this, we're going to discredit this one. So we don't count that one. Doesn't make sense because it's going to be negative time, right? I always like to do a visual whenever I can. All right. Looking at the expression, ladies and gentlemen, we have decimals. So I'm not even going to worry about trying to factor. I'm just going to go with quadratic.